And we're on.
Okay. All right.
I'll
Well,
paste the chat for people who want to enjoy the show.
very good.
Just a second.
So on YouTube, the slides will automatically play.
Yeah. I'll be playing the slides. Yeah.
Oh, okay.
Yeah, that's
Sounds good.
that's the essential feature. So if you want to enjoy the show without, without wanting to participate, and then you don't want to keep flickering between Clubhouse and the slideshow,
Okay.
then you can just open on YouTube and chill. And if you type a comment, I will be able to hear you. Of course, if you want to participate live, then you have to show up in Clubhouse.
Yeah, so I hope you guys are all in Clubhouse listening to this so you can participate in the conversation and it's not going to be just one person yakking. For those of you who are here, the slides are pinned to the top of the page. And so let's start. So this is, I'm just reviewing what I've done through the end of 2024, and I looked, and in 2024 I only gave five five lectures, right? I was doing them. It was supposed to be weekly, so of the 52, I only fulfilled five of them. So hopefully 2025 will be a much better year for the chemistry series. All right, so let me come here. The slide numbers, I'm very sorry, they're all over the place because I just took the slides from various presentations, and I forgot to go back and change the slide numbers. So when I say slide number, it's the location of the slide in the slideshow and not the slide number that says on the slide itself. So sorry about that. Anyway, so we basically talked about that chemistry in essence is really the science of following electrons. That what we as chemists do, whether we're synthetic chemists, structural chemists, physical chemists, analytical chemists, however you want to classify us, what we're doing is we're following electrons and trying to figure out how they move within a molecule or within an atom. And so we basically live with electrons. The nuclei don't get involved, not that much. The protons tell us what the charge on the particle that we're looking at is. Is it neutral or is it a cation or anion, that is a positively charged ion or a negatively charged ion? And the neutrons are there that the sum of their number with protons gives us the atomic weight of that particular atom, which allows us to calculate the molecular weight for the molecule we're dealing with. And so if you're doing any kind of synthesis, any kind of analytical chemistry, you have to work with moles, not with grams. And so you need to know the molecular weight, which is grams per mole of the substance. So then on the next slide, we went ahead and talked about the current model of the atom, which is the Schrodinger model, and solving the Schrodinger's equation for the hydrogen atom, we get these nice looking orbitals. We said each orbital is the area of 50% probability of finding an electron in that space. So it is not a well-defined space. It is a cloud, but we just draw a line around the 50% probability space. And we talked about how these orbitals get Field and Hund's rule, etc. Really basic chemistry and physics stuff. On the next slide, we introduce the valence shell electron pair repulsion theory, or the VSEPR theory, that lets us know kind of on a first approximation what the shape of a molecule is. And so when we're in organic chemistry and we're trying to do synthesis, we're very much interested in the shape of the molecule, because that tells us whether there is space in that active area of the molecule, whether there's actual physical space for the attacking moiety to fit in and make the chemistry happen. So we need to know what the shape of the molecule is, and VSEPR is one of the easiest and simplest approximations that we can have. And so on the next slide, which is now the fifth slide in the whole series, the AXE system for having 2 to 6 substituents around the central atom are shown. And we discussed that for carbon compounds, we really only have 2, 3, and 4. We almost never have 5 things around the carbon atom, and absolutely never do we have 6 things around the carbon atom. So the 5 and 6, the last 2 rows, don't apply to organic chemistry. When we are dealing with carbon in its fully saturated form, meaning that all the bonds to the carbon are single bonds, we're in 4. The first one, 0 lone pair, which is a tetrahedral structure. When we have a double bond, we go to 2, which is the trigonal planar structure, and when we have a triple bond, we go to 2, which is the linear structure. The next slide, we introduced molecular orbital theory. This is a more rigorous theory of bond formation than VSEPR. And so it is completely based on quantum mechanics. VSEPR is not based on quantum mechanics. It's completely Newtonian. It only deals with basically spaces and electromagnetic repulsion, attraction, things like that. It doesn't involve quantum mechanics, but molecular orbital theory involves quantum mechanics, first by calculating what the atomic orbitals are going to look like, and then what the molecular orbitals are going to look like. So in the next slide, 7th slide, we showed pictorially what bond formation under molecular orbital theory looks like. So this is sigma bonds that I'm forming between either 2s orbitals or between hybridized orbitals. And then on the next slide, that's the mathematical representation of a sigma bond for the H2 molecule, where on the left-hand side and right-hand side we have atomic orbitals of the hydrogen. And when we add them together, because we started with 2 orbitals, we have to end up with 2 molecular orbitals. So when we mathematically mix them together, we end up with 2 molecular orbitals that are at different energy levels. So we start with 2 atomic orbitals at the same energy level, and we end up with 2 molecular orbitals at different energy levels. So as you see, the sum of the energy levels are the same. It's just that one went down, became negative, one went up and became positive, but the total sum is the same as what we started with. The lower orbital, where is of lower energy states, both electrons, one from each of the hydrogen atoms, goes into that. That is called a HOMO, which is the highest occupied molecular orbital. And the top one is a high energy orbital. In this case, is unoccupied. That's the LUMO, which is the lowest unoccupied molecular orbital. And the bottom one is a sigma orbital, which forms a sigma bond. That's a single bond between the two hydrogen atoms. And the top one becomes what we call sigma star. It's the anti-bonding orbital. And if you populate the anti-bonding orbital, then you start to breaking the bond. On the next slide, I showed you a more complicated molecular orbital. This is for CO, for carbon monoxide, because I just showed you as an example that carbon and oxygen start out at different energy levels. Their atomic orbitals, because oxygen is more electronegative, has greater affinity for electrons, so the energy levels for its electrons are lower than that of carbon. But again, we mix them together. Here it's more complicated because we're mixing 2p orbitals as well. So we have a sigma bond and 2 pi bonds, as this shows, and there are 2 orbitals in a sigma star antibonding orbital. Those are the electron pairs that we see, and then the upper ones are unoccupied. Then on the next slide, we introduced pi bonding, because in the molecular orbital picture I talked about pi bonding. So here pictorially we're talking about pi bonding in ethylene, or ethene, CH2. We said a sigma bond in the middle is formed by the overlap of sp2 hybridized orbitals. But we also have unhybridized p orbitals that are vertical to the plane of the molecule, and those overlap the unhybridized p orbitals, and that overlap forms the pi bond. So when we have a double bond between carbons, or carbon and something else, one of the bonds in the double bond is a sigma bond, which comes from the overlap of the hybridized orbitals, and the second one is a pi bond, which comes from the overlap of the unhybridized p orbitals. In a triple bond, then there's another unhybridized p orbital which overlaps, and that's again perpendicular to all of these. So if we say the CR prime R is in the xy plane, then the p orbital would be in the in the z direction, and then the other one would be in the x direction, coming out of the plane of the paper. So then we said, when we have this overlap of p orbitals to form a pi bond, what if I have another atom next to it that also has p orbitals? Can that overlap with this? And that next slide, which is slide 11 in the deck, or the 11th slide in the deck, we introduced the concept of resonance, where we have 2 double bonds that are interspersed by a single bond. We'll see here that all 4 of these carbon atoms have vertical p orbitals, and so they overlap with each other. So we end up really with the structure that's at the bottom, meaning that we form a chain of sigma bonds but then the pi bonds are basically floating all over the molecule. They're not localized as the pictures on top are showing. That like in the top left, I'm showing there's a localized double bond between carbons 1 and 2 and a localized one between 3 and 4. We'll see that that's not the case. And how do we know that's not the case? We know what the bond length for a carbon double bond is, what the length is. It's in a range. And we know what a single bond, carbon-carbon bond, the length of it is. And so here in propane diene, well, which is the molecule I have shown you, if we crystallize it and get the bond lengths, or we do that through spectroscopy, we'll see that all three bonds have exactly the same length. So we're not dealing with localized double bonds and single bonds. We're dealing with a delocalized kind of like 1.5 bond kind of a thing. And so on the next slide, I showed that this can happen even if we don't have all carbons. So oxygen, because it has p orbitals that are unhybridized because of its electron pairs, the lone pairs, we can form the same resonance structures with oxygen as well. And so these things that I'm talking about now are kind of very important concepts that we'll see over and over and over again, and that's why I included them in the review. If you guys have any questions, please come up and ask them, and or you can wait until we're done and ask your questions, whatever. Hello, one.
Hey Sam, it's Jacob. Sorry, I have a new phone.
Oh, okay. Hi, Jacob.
Hello. My question is, it might not be extremely relevant to the today's current presentation, so I can wait. It's more about. I was gonna request if you could do more nuclear type of conversations and make people understand like the safety of nuclear energy and things like that, and maybe I can bring some people that have experience to help with that.
Yeah,
But I can wait for that.
I don't know nuclear chemistry, and I think, I mean, I had a class in it back when I was an undergrad, but this is like almost 40 years ago. I don't remember any of it.
When you
So
said
if you,
pi and sigma bonds, I was like, oh man, I forget my chemistry. I had to look at the slides.
yeah, so if you have people who know nuclear physics and want to give presentations, we're more than welcome to invite them and give presentations.
I'll
Yeah,
ask them to I'll ask them to link up with you and send you a message or something.
thank you. Yeah, that's nuclear physics is completely outside of my wheelhouse, so I won't.
I'm sure there's nothing really outside of your wheelhouse,
Oh,
Mr. Sam.
no, there is.
But I feel like in the future, I feel like society wants to make a transition to nuclear energy, but we simply do not understand it. And
Yeah.
it's like I feel like you would be a very good like host to help introduce that type of concept. Yeah.
Thank you. Well, we'll get. All right, so moving on, I'm on the 13th slide in the deck, the purple benzene structure. That's the benzene molecule. And on the left-hand side, you see the two resonance structures. We call them Keckley structures. Keckley was the chemist who figured out the concept of resonance, and he actually dreamt about it when he fell asleep on the bus going home. He was trying to figure out how uh, how benzene works, and he fell asleep, and he dreamt that one end of the molecule turned into a snake and started eating the other end of the molecule, and it's like, ah, it's a ring. And so when he got home, he worked out the structure of benzene. So uh, I've shown that on the left-hand side are the two resonance structures, shows the double bonds and single bonds. But again, we see that in the structure in the actual structure of benzene, all the bond lengths are exactly the same. So all the bonds are the same. We don't have alternating single double bonds, and so this is basically just a cloud of electrons in the overlapped pi system. And then on the next slide, I introduced the concept of dispersal of charge. And I said that's an important thing. The example that I have up there on the top, we have a carboxylate group, which is a deprotonated carboxylic acid, and the bottom we have a deprotonated ethanol. And so we see that on the bottom one, the negative charge is localized on the oxygen and doesn't move around at all. But in the top one, the negative charge can be on both oxygens because of those resonance structures that I can draw, and it would also partially be on the carbon because the electrons are moving within that pi system that I was talking about. We have 3 atoms with p orbitals that are all overlapping with each other, so the negative charge is within that sea of electrons, and so it's dispersed over 3 different atoms, and so we see that when we can get the charge dispersed over more atoms, we end up with a more stable situation. So acetates or carboxylates are pretty stable, whereas oxides are not. So then that led directly to acid-base chemistry because of the deprotonated ethanol that I showed, the ethanol that had lost its proton or its hydrogen plus. And so we said that in chemistry we have 3 different definitions for acids and bases. One is the proton exchange definition. So an acid is a proton donor and a base is a proton acceptor. The second is a Lewis acid-base definition, which is electron pair exchange. So acid is an electron pair acceptor and base is an electron pair donor. And the hydronium ion concentration definition. This only happens in aqueous solutions that are water-based. So acid increases the hydronium ion concentration and base lowers the hydronium ion concentration. Hydronium ion is H3O+. So if you take water, water dissociates by one of the water molecules, donates one of the H's to another water molecule, so you end up with OH minus and H3O plus. So water, just pure water sitting there has about 1 times 10 to the minus 7 moles per liter of H3O plus and 1 times 10 to the minus 7 moles per liter of OH minus. And it's the concentration of H3O plus. If you take the negative log base 10 of that, that gives you the pH. So because H3O plus concentration is 1 times 10 to the minus 7, negative log base 10 of that is 7, so pH 7 is neutral. So that hydronium concentration only happens in water solution, in aqueous solutions. Then we just quickly talked about carboxylic acids getting deprotonated the same way that water gets deprotonated. And in the middle of that reaction, you see that the arrows go both ways. When chemists show the arrows going both ways, it means that the reaction can proceed both in the forward direction and the reverse direction. And what happens is that you end up with a situation where when the rate of going forward is equal to the rate of going backward. So if you look at the concentrations of these species, they don't change. But if you could somehow label them, you would see that the label keeps moving around because the carboxylate keeps getting protonated, goes to carboxylic acid, and that keeps getting deprotonated, going to carboxylate. We talked about acid-base reactions and introduced what pKa is. pKa is important when we start talking about biologically active compounds, because the higher the pKa, the higher the pH needs to be to protonate it. So if something has a pKa of 10, then I know that under normal pH of 7, that thing has the proton on it. It's not off. And so knowing the pKa tells you what species you're dealing with in the solution. Are you dealing with the protonated species or the deprotonated species? And that changes the chemistry that they do. And so we'll see this concept of pKa in the future. And when you talk about the acids and bases, you have to talk about salts. So a salt is obtained when the H plus of an acid is replaced by a metal ion. So HCl, if I react HCl, which is hydrochloric acid, with NaOH, sodium hydroxide, the hydroxide grabs the proton of the HCl and forms water, and you end up with NaCl. So now sodium has replaced the hydrogen and has given us NaCl. Every time you take a proton off and you put a metal ion there, that becomes a salt. So, or the other way around, you take an H minus off and you put a negative ion next to it. So if you kind of read your shampoo bottle or whatever, you see things like sodium laureate. Well, what is sodium laureate? Sodium laureate is the sodium salt of lauric acid. So it's a carboxylic acid. You take the H off, put sodium there. So a lot of these, you have seen a lot of these things in everyday life. The next thing that we talked about was the chemistry of the alcohols. Ethanol, we used it as an example, and they can act as both acids and bases. On the top, ethanol is functioning as an acid. It's donating a proton to a base, and on the bottom reaction, it's acting as a base. It's accepting the proton from another molecule, or you can say in the top one, it's accepting the electron pairs of B, and therefore it's an acid. That's the Lewis acid-base definition. On the bottom one, it's donating an electron pair to the H+, so it's a Lewis base.
Sam, do you have any Do you have experience with biological reactions of
Yep.
these types of alcohols?
Yep.
Is
What do
there
you?
something, well, is there something that you could share that what happens internally in our systems when if we consume alcohol, for example?
Oh, yeah. That's pretty complicated.
Maybe we could do a series on it or an
Yeah, yeah,
episode on
yeah.
it.
We are. So I'm running another series, also the pharmaceutical series, and so something like that would be discussed there because that talks more about biochemistry. This is more of organic chemistry for now. In the future, it will go into biochemistry, but more into DNA chemistry as opposed to uh, other kinds of stuff. I mean, alcohol is complicated because you have both alcohol itself that is acting, then you have an oxidation product of ethanol through liver cytochrome P450, and then you have the metabolic products of ethanol through glycolysis. So all of those basically join forces to give the effects that you see in alcohol. So that's why I say it's a complex. It's not just one reaction that we can talk about.
Did you say
It's
P450?
Yes, cytochrome P450 is a family of enzymes in the liver that they oxidize organic compounds, and that allows them to become solubilized in the blood and get secreted through the kidneys and urine. So that's how we get rid of poison in our body. And so cytochrome and also alcohol dehydrogenase, that also in the liver, both of those work on alcohol. So things become complicated.
The only P that I've ever memorized is the P53. You know that one?
No, I don't know what P53 is.
It had a common lingo of our, it says, oh God, I forget.
Is it in the cytochrome family?
No, it kills cancer. P50.
No. P53
It's like
doesn't kill.
our guardian angel cells.
Yeah,
And then what I learned one time in pathophysiology is we create point mutations, and then when over 50% of our P53 proteins are kind of mutated, then it's like the official
yeah.
start of
No,
cancer.
P53 is a protein.
I see Siran laughing. Siran, if you have if you have information on this, I would love.
P53 disrupts apoptosis. So when you get high concentrations of P53, your cells become immortalized. They become cancer cells. That's one of the mechanisms of immortalization. And so there's certain anti-cancer medications that basically sequester P53 in the cell. So that induces apoptosis. So cells can then go ahead and die, and they won't become cancer cells. That's totally different than what we're talking about.
Yeah. Sorry, I just when you said P and then a number, I'm like, hey, I remember P53.
Yeah.
So I just wanted to share it.
Sure. All right. So on the next slide, we continued with the reactions of alcohols. How we prepare them is by reactions with hydroxides or water, as we've shown them. These types of reactions are pretty important in biological processes. And on the next slide, which is the 21st slide in the deck, I introduce the terms nucleophile and electrophile. These two words are used extensively in organic chemistry. A nucleophile, nucleo means nucleus, so it's nucleus loving. It seeks positive charge. And an electrophile, electron loving, it sees a negative charge. So if I go back to slide 19 again, where I used ethanol as acid and base, in the top reaction, base is a nucleophile. The B is a nucleophile. H is an electrophile because B is being attracted to the proton, to the nucleus of the hydrogen, and the hydrogen is getting attracted to the electrons of B. Whereas in the bottom one, O with its electrons, that is now the nucleophile because that electron pair wants to go after the positive charge of the sorry, the arrow here is incorrectly drawn. When I moved these around, the arrow has to go to the H, and so oxygen goes after the H, and so oxygen is a nucleophile, H is the electrophile.
So the BH has to move a little bit to the left because I can correct it now. Yeah, okay.
Yeah, it needs to go to the left. So that the arrow is pointing to the H.
Yep, fixed.
Okay, thanks. All right, so going to so nucleophile and electrophile discussion always leads to discussion on carbocations on slide 22. Cations are positively charged particles because cathode in a voltaic cell is the negative end, and anode is the positive end. So the ions that move towards the cathode, which is the negative end, are called cations. So those ions are positively charged. So the cat comes from cathode. And then when the carbon atom is bearing that positive charge, because it's a carbon that's a cation, we call it a carbocation. It's not carbocation, it's carbocation. When George Olah at USC won the Nobel Prize in chemistry in the mid-90s, he was the god of carbocations. Almost all of the carbocation chemistry that we know of came from George Olah. And so all newspapers or TV news people called it carbocations. And so we had a good laugh, but don't call it carbocations. That was a nerdy joke. So we can have primary, secondary, tertiary carbocations. Goes and as we go to the left, the stability increases, which kind of makes sense because there are a lot more things around the carbon that protect it from other chemicals to attack it. So basically, carbocation formation is again one of the most common biologically related reactions that we see. So we finished the structure of the conversation on alcohols, and we move to the next big basic structure, which is that of an acyl group, C double bond O. And on slide 24, I'm showing you all the various acyl families that we have. aldehydes, carboxylic acids, amides, acid halides, ketones, and esters. Under physiological conditions, so in your body, in everything that we eat, in everything that we drink, if there's a carboxylic acid, it is deprotonated. That is, it's in the carboxylate form, which is I've shown in the bottom right. It is rare that we run into a carboxylic acid in our daily life in its acid form, mostly because the pH that's required for the carboxylic acid to remain protonated is too high for us to eat or deal with in any shape or form. So if you guys are have ever used like 45% or 60% vinegar as a weed killer, that the acetic acid there has a fair amount of the carboxylic acid. But the vinegar that we get from the store for salad dressing is all carboxylate. Anyway, the next slide, these are condensation reactions for both amides and carboxylic acids. Sorry, it's carboxylic acids that react with alcohols, form esters, and carboxylic acids, when they react with amines, they form amides. Why are amides important? They're important because a peptide bond is an amide bond. So all the bonds inside of proteins are amide bonds. And why are esters important? Because the bond within your DNA is a phosphodiester. So it's an ester bond that one side of it, instead of being a carbon, is a phosphorus, but it is an ester group. So these two reactions are of paramount importance in biological systems. As you can see, the arrow for both reactions, both forward and backward, when it goes forward, it's called condensation. Well, because what is condensation? Condensation is when something condenses down and you form water droplets, right? And so here, condensation, you turn two molecules into one and you form water. The reverse reaction is hydrolyzation. Hydro is water, lys comes from lysis. In Greek, that means breaking. So hydrolyzation means breaking with water. So basically, I'm breaking the ester bond or the amide bond by inserting the water into it in the reverse reaction that I've shown. So condensations and hydrations are reverse processes of each other. And then the last slide, the acyl chloride. Rare you run into an acyl chloride in biology or biochemistry, but in organic chemistry, they're one of the most important starting materials for synthesis and making of new things, because as you can see, you can do a whole bunch of stuff with them to get a whole bunch of different types of compounds. So this concludes my review. Next time we meet, I'm going to start on, I'm going to leave reactivity for a little bit and start on thermodynamics. We basically, hopefully you guys were around Friday for John's resonance talk. If not, please go ahead and check the recordings of that, because that is really where a discussion on thermodynamics and chemistry starts, with bond vibrations. And so, yeah, let me see. Shamash, do we have the link to
Sure.
John's?
This is the link to the YouTube channel. You can find a lot of the past lectures that we've done, whether it's John or myself, and I will link to the last live we did on resonance specifically right now
Okay, great.
in chat, resonance room. There you go.
Yeah. All right. So I don't have anything else to add. Just come on up if you have questions, and we can talk about chemistry. We can talk about science. We can talk
Do I get to go back like to slide 7?
Sure.
There's no going back ever. No, I'm joking.
That's it.
All
Like
right.
it's like a pawn. It moves forward.
Yeah.
I missed molecular orbital theory. I'm not familiar at all with this section because probably I missed the room when you did it. So I'm looking at all of these, and of course I recognize the letters. So these are the letters that we learn in elementary chemistry when we're trying to count the orbitals in every electronic shell. But what are these shapes? Can you elaborate a little bit more? Like what is this about? And because I'm familiar with Vesper, so the concept is we want to maximize the space between electrons. So we don't want electron orbits to be next to each other. What's the idea behind this molecular orbital theory?
Sure. So Vesper actually doesn't deal with orbitals at all. Vesper wants to minimize electron repulsion based on electrons that are either in bonds or in unbonded electron pairs. Okay, so you just want to push those out as much as possible. You don't care where those electrons are held, as long as you basically physically know where they are. Molecular orbital theory tells you where those electrons are. Okay, so once I solve the wave function for the particular electron in the particular orbital that it's in, I will end up with a space where the electron wave can exist in that space. Now, theoretically, that space is infinite because that wave can be anywhere. And so that doesn't really help us anything because even though it can be anywhere, the further you get from the nucleus, the probability of wave being there becomes less and less. So what I do is that I draw a 50% probability line. That is inside of my line, I have a 50% probability of finding the electron there. And outside of the line, which extends to infinity, I have 50% probability of finding an electron there. So this kind of gives me a kind of a spatial picture for me to work with. Now, when we form molecular orbitals, we start with atomic orbitals. These are orbitals on the atoms where the electrons on the atom sit. But when we bring the two atoms together, we see that the electrons move and form what we call bonds, right? Well, based on molecular orbital theory, electrons can only move within an orbital. So what is this orbital? This orbital becomes a mathematical addition of the orbitals of the two atoms that come together. Now, sometimes this addition can take place because they're orthogonal to each other, or they are, there's some reason that you can add these two matrix algebra variables that you have. You can't add them together. So what you need to do is before you form the molecular orbital, you have to change the orbitals on each atom, meaning that you have to take the S and the 3p's or 2p's or whatever, however you're doing, and mathematically first add the S and the P orbitals to form a new shape. Now, if you've used all three orbitals in this addition, the result that you get are 4 sp3 orbitals. If you used only 2 p orbitals in this mathematical amalgamation, you end up with sp2. If you only used one, you end up with sp. So the sp3, sp2, and sp orbitals are, when you look at them from a chemistry moving forward point of view, they are just a single symmetrical lobe that you're looking at. Okay? So in this slide, slide 7, that I'm showing you, these are all the various forms of single symmetrical lobes that you see. So on the left-hand side, you have 2 s orbitals. Sorry, I kind of, I jumped a few steps. I apologize for that. Hold on a sec. So now, when we go to form a bond after we have done this hybridization, this mixing of orbitals within a single atom, now we go combine these two together and they overlap. What does overlap mean? Overlap can either mean a physical overlap that they're overlapping, or it means a mathematical addition if you're a theoretical one. So once we add them together, you end up with a single molecular orbital in the bonding region and a single molecular orbital in the antibonding region. That's in the next slide that you see. So that is the mathematical addition to form molecular orbitals from atomic orbitals. So basically, to form that, we did 2 mathematical iterations. One, we mathematically added the orbitals within a single atom, and then once we do this with the different atoms that are going to form a bond, we mathematically add the atomic orbitals of those 2 atoms to form a molecular orbital. So far with me, Shamash?
Yeah. So if we have the first example, let's say that's SS, right? So on the slide 8, you take the example of an H2 molecule.
I haven't gotten to the slide yet.
Okay.
So far, everything I gave was background to what I'm going to get to the slide. Okay. So far, we're okay with hybridization in an atom and the addition of atomic orbitals to form molecular orbitals.
Absolutely.
Okay, so now, how are these orbitals between the 2 atoms are going to get combined, right? You can come at each other in 2 different ways. So in that slide, let's look at the top right, PZ shape, okay? If I'm bringing 2 p sub z orbitals together, I can do it in 2 different ways. They can either come at on a line like it's shown, or they can be vertical and come at each other, kind of like the 2 dark orbitals right below them, right? Those are, so if, again, we look at the dx squared minus y squared, dx squared minus y squared picture, bottom right-hand side, we see that 2 of those come at each other on a line, but then 2 of them are coming at the dark ones are coming at each other sideways. So we can have 2 different types of overlap between orbitals. One is that only one lobe of one overlaps with one lobe of the other, or two lobes of one overlap with two lobes of the other. Okay? Both of those, the opportunity for both of those are shown in the bottom right picture. The white ones are coming at each other so that only one lobe overlaps one lobe, but the dark ones are coming at each other where the top lobes overlap and the bottom lobes overlap. So two lobes overlap each other. So a sigma bond is any bond that's formed between any type of orbital where they come together and one orbital overlaps one other orbital. That's the definition of a sigma bond. So what this slide shows is that it doesn't matter where that one orbital is coming from. It could be an s orbital, could be a p orbital, could be a hybridized orbital, unhybridized orbital, d orbital, d with z, d with s, d with p, p with s with s, it doesn't matter. As long as you have one orbital overlapping one orbital of another atom and no more, you have a sigma bond. If you have two lobes overlapping, you have pi bond. So you have, depending on what elements you're working with, you can have two bonds, 1 pi, 1 sigma. You can have triple bonds, 2 pi's, 1 sigma. You can have quadruple bonds, 3 pi's, 1 sigma. You can have quintuplet bonds, 4 pi's, 1 sigma. You get those in transition metal chemistry where you involve f orbitals into bonding. So basically the take-home lesson is one orbital lobe overlaps one orbital lobe. That's a sigma bond. Two orbital lobes in a vertical fashion overlap two vertical lobes, you get a pi bond. Questions?
So this is what we're seeing on slide 10. So the two electrons shared between the CO are in the same horizontal elliptical orbit.
Right.
So that's why this is a sigma bond. Whereas even if we have two different electrons, but they are in two different lobes, so that's why this is a pi bond.
Yes, exactly. So
the number of electrons is irrelevant. It's if where they are in the same thing or not.
No, well, you can't you in a bond you must have two electrons, no less and no more. If you have more than two electrons in a bond, you don't have a bond. If you have less than two electrons, you don't have a bond. So you always have two electrons, but so you have two electrons in the sigma bond, and you have two electrons in the pi bond.
Okay, is it not possible that in the CO example, let's imagine it's two different atoms. So if you add a black dot on the left and a black dot on the right, so two electrons from the left are bonding with two electrons on the right in the same orbital lobe, is this not possible?
No, not in the same orbital lobe. So if you have four electrons, you have to form two molecular orbitals out of four atomic orbitals. Two molecular orbitals out of two atomic orbitals. You can't put four electrons into the same bond, meaning into the same orbital overlap.
Is it because of the Pauli exclusion, or is it some other reason?
Yeah, okay. No, that is Pauli exclusion principle. Exactly.
Got it. Wow. Okay. Thanks, Sam.
Sure. Okay. So here's a kind of a administrative bookkeeping thing. I have both the chemistry series and the pharma series, but it's too much for me to do 2 rooms in a week. Should I stagger them? 1 week this, 1 week the other, or just do one, finish it, then do the other? What do you guys think?
A classical double bond Prof. Staggering might work, or if you can find another molecule to help.
Sorry, I have a hard time hearing you. There was a lot
Sorry,
of
my
garbled.
audio.
Yeah, it's very garbled. So what do you think, Shamash?
I'm more of a classical guy. I'm more for let's do one topic once a week and then finish it and then move to the pharma.
Okay.
Simply because people will forget, like
Yeah.
the 2 weeks, and because you will rely on what happened previously. And we are not in a classroom, so people will not be doing homework over the week. So
Yeah.
we will
Yeah,
totally forget what you were talking about. I think this is for the best. I'm not sure if people have opinions. Please say in chat or just come up.
All right. Okay, so Abyss has asked if I can talk about alkyne bonds. Yes, absolutely. So let's stay on the slide that we're on. That is the 10th slide in the deck. That's the one that shows the bonding for an acyl group, the C double bond O. And so here we see that both the carbon and the oxygen are sp2 hybridized. So we have three sp2 orbitals in the same plane, in the plane that's perpendicular to the plane of the paper. We have 3 sigma orbitals there. One of them is involved with sigma bonding with the R group. Another one is involved with the sigma bonding with the R prime group. And the third one is the one that is pictorially shown, is in a sigma bond with the oxygen. Now, these are sp2 hybridized, so there's a p orbital that is not hybridized, and that p orbital is sitting there perpendicular to the plane of the molecule, which means along the plane of the paper. So it goes up and down along the plane of the paper. Now, we said that the overlap of these 2 p orbitals forms the pi bond, which, in addition with the sigma bond that we see, forms a double bond. Now let's turn the oxygen to the right to a carbon. Okay, nothing changes. It's just that O turns into a C. And now let's remove one of the sp2 orbitals. And so we're going to be sp hybridized, 1s1p. That gives us 2 sigma bonds. One is basically the same sigma bond that we see with oxygen here. That's going to be the sigma bond between the 2 carbons. The other one is going to be 180 degrees from that, meaning that it's going to go between where you see R and R prime. So the bond angle there is going to be 180 degrees. Now you have 2 unhybridized p orbitals. One is just as shown in the plane of the paper, and the other one is going to be perpendicular to this and perpendicular to the line of the sigma bond. So it's going to be coming out at us and go into the plane of paper. Both of them are going to have that, so those 2 are going to overlap and form another pi bond. So in a triple bond, what we have is a central bond in the center, which is a sigma bond. Then we have two p orbitals overlapping for one pi bond, and perpendicular to that is going to be another two p orbitals overlapping to form another pi bond. That forms the triple bond, carbon-carbon triple bond, or carbon-nitrogen triple bond, carbon-oxygen triple bond. That's how it's done. Abyss, did I answer your question? Okay. No, that's fine. That's yeah, that's why we're doing this. Everybody's a chemist rusty.
So Sam, do you have like a Google file where you keep all the slides?
Yeah, I have a Google Drive for that. I should give you the link to that, huh?
Yeah, if you could do that for me, so we can put it in the video description, so that people could refer to it.
Okay. Yeah, I'll do it. I'll do it after we get off because I need to clean it up or put it into another.
Yeah. All right, cool.
Yeah, I don't have the sound, the voice files, but
No, we don't need the voice files. When I get time, I'm gonna download them from Clubhouse and upload past episodes that I feel are useful. But there's no way we could upload everything, so we're gonna start the clean work from now on. You know what I mean? And whatever back work we can do, then we'll do it.
sounds good. Oh, sorry. Okay, are there any more questions or?
Kirko wants to
Hi,
speak.
Kirko.
Hello, yo, I do have one like random quick question. Um,
Please.
so it was always kind of confusing when you talk about like electron orbitals, not like you per se, but in general, because like you'll have like an atom that like for example, carbon has like four in that outer shell, and there's like a different like set of like it has its own like I guess orbitals. But then you go to like a different one like oxygen, and you add like what like two electrons, and now like the outer shape, like when they talk about like what is capable of bonding, it's like different. But like it's not as if the capacity for the outer shape changes between like these two atoms that are like two apart from each other on like the periodic table. Like that weird like fact is always kind of like bugged me, and I felt like maybe it's because it was like something I was misunderstanding.
What do you mean? What do you mean
So
the capacity
so like
changes?
it doesn't change. So like for example, uh both like atoms kind of have this for lack of better terms innate desire to have like eight electrons in their outer shell, if I'm correct. I can't remember like precisely like
Yeah,
everything.
that's correct.
So but like when you look at like the bonds that they form, and like the directions in which these uh the atoms take when they bond to like for example oxygen or carbon, it's not like the same. You know what I'm saying? Like if you take like was it methane? Yeah, methane. So it's carbon and like four hydrogens. They're like kind of have this like tree like type structure. At least that's what you're taught like back in school. But then like you look at oxygen and like for like water or something, it only has like two I guess like loose electrons for bonding. it's like not that. Like how do I put it, man? I'm trying to like put these into words. I haven't thought about this in forever. So like you have like your hydrogens that are like kind of like it's like a Mickey Mouse. You know what I'm saying? Like, and the other two valence electrons like are like opposite of like the hydrogen. So it almost looks like the patterns forming an X when you draw it out versus like the Christmas tree for like carbon and methane. But like they want the same number of electrons like in that like outer shell. You know what I'm saying? Like it that always bugged me. I hope this is like making sense because it makes sense when I say it, but I don't know if it makes sense with now that I'm saying it.
It makes perfect sense. So let's whenever you get a chance, go look at the fifth slide in this presentation, and that shows the structures of compounds in the AXE system. So what happens is that both water and methane are tetrahedral structures. So basically, the basic structure is the same, but why is it that one is bent but the other one looks like a tree? It's because of exactly what you said. It's because carbon has 2 less electrons than oxygen. So oxygen has 6, carbon has 4 in the outermost shell. So if oxygen wants to get to 8, it only needs 2 other electrons. So it just grabs 2 other things, 2 hydrogens, let's say, and shares the single electrons on that hydrogen, and it gets to 8. But carbon, which has 4 electrons, in order to get to 8, it needs to have 4 things around it. That is, share electrons from 4 hydrogens. So it ends up with that tree-like structure that you're talking about. So those two electrons really play a huge role in how. So then the next one, right, is nitrogen. Nitrogen's right in between them. Carbon has 4, oxygen has 6, nitrogen has 5. And so nitrogen has 3 things around it. That's why ammonia is NH3. It has 3 hydrogens around it. So you go CH4, NH3, OH, and then HCl. Chlorine has 7 electrons, so it only needs 1. As you go across, the number of hydrogens goes down. Did that make sense?
Yeah, like I guess like the where I'd go from here is like if the the goal is like a full shell, and like I can loosely remember this the how the orbitals are placed is something to do with like maximizing like the distance between them from like the whatever repulsion, the electromagnetic repulsion of the electrons upon each other.
Hold on. You're combining 2 separate topics now.
Well, no, I know, but like it's coming like right back to this because like yeah, I just trying to remember things clearly because I haven't taken chemistry in like a decade. But like the if the actual placement of where these orbitals quote unquote are supposed to be uh has some like something to do with like the uh like I guess these electrons being as far away from each other as possible. Like I don't understand that why that would change in between all of these like different atoms from like uh let's say just carbon to chlorine when I mean theoretically if they're fully bonded they have the same number of electrons in that outer orbital. Does that make sense?
No, it didn't.
Okay, so like let's say I have methane and hydrogen chloride, like both of them like technically like with their bonds have 8. But like if you were to like draw out like I guess like is it the Lewis structure where you like have like you draw like the little electrons around and you put the bond for the other atoms that are bonded to it. Like when you draw that out, like you'd have like a carbon with a hydrogen going up, and one going to the hydrogen going to the back at the bottom, then one going to each side, or one going forward and one going to the side. But then like for the hydrogen chloride, you just draw like the Cl dot 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 up H. You know what I'm saying? Like it doesn't look like it's the same structure in like 3 dimensions, I guess.
Well, in HCl, you only have 2 atoms, and so you end up with a line. There isn't. I mean, there isn't much you can do when you only have 2 points. You can just draw a line. So any molecule that has 2 atoms to it is necessarily linear. But when you have 4, now you have options of how you're going to put these 4 around the atom. And so in carbon, in its most reduced state, like methane, it's all going to be tetrahedral, which is what you said. One goes into the page, one comes out, one goes up, one goes to the side. So that all of that has to do with how many things you have around the central atom. Yeah, really, if when you get a chance, you get somewhere, you can take a look at the slides. Look at slides 4 and 5 in this presentation, and I think that would answer some of these. Oh, no, I don't have a background in computational chemistry. I have used StatMech to determine diffusion rates, but not at the thesis level, just as an undergraduate lab experience.
Thanks for that.
Sure.
Yeah, because like that was also one of my interests as I was working on the thesis, as I mentioned. The other thing that I was interested in, I don't know if this is also something that you explored, was intermediate products that actually kind of last for, they're barely detectable, right? Because they last for about like femtoseconds or something like that. So that was also my interest in kind of advancing this, but I don't know if that's something that you worked on before.
Yeah. So the my session starting next week, as I said, is going to deal with thermodynamics. So I'm as part of that, I would be kind of defining what a transition state is. And so part of that definition is that if the transition state has any detectable life, then it becomes an intermediate, and definitely has a local minimum there. But if so kind of distinguishing between what's a transitory intermediate and what's a transition state. Those are different things, and so I would be talking about it in that context in the next few weeks.
Sounds good. Looking forward to it.
Thank you. All right. Well, we've been at it for an hour and a half. Thank you very much for staying with me as long as you did. And don't forget John's rooms on Fridays and Shamash's philosophy of science rooms on Wednesdays. Shamash, do you want to give more information about your room?
Sure. We're running a philosophy room every Wednesday at 17:30 GMT. That's what is it? 9 Eastern, 9 a.m. And at the same time, also on Friday with John. My rooms are more about mathematics and philosophy of science. We talk about various issues in philosophy simply because this was motivated because we have a crowd of scientists here, and they kind of they make bad comments about physics, about philosophy. So I was motivated to start this series, and we're having fun. Last week we were tackling issues in ontology of science. So what is it that we consider to be real and what is not? Specifically, it was about this specific thesis in the philosophy of science, which states that everything that is real will interact with us at some point. So we were kind of discussing that idea. And this week, this Wednesday, we will be talking about a historical movement called the logical positivists. So those people believe that meaning can only be established through physics, and everything you talk about must have a physical interpretation somehow. So we will explore this idea more and more, see where it goes. Yeah, this is in short the series.
Awesome. Thank you very much. You don't know this, Shamash, but as an undergrad, I was a philosophy minor. And the reason I didn't become a chemistry philosophy double major was because at UC San Diego, philosophy major required a year of Latin or Greek. And
as it should.
As it should, exactly. And I wasn't willing to take a year of Latin or Greek. So I ended up with a minor. But don't ask me to. The other thing is, I was being highly recruited by one of the philosophy professors to go to grad school in philosophy. And as I was contemplating that, my girlfriend at the time, who is now my wife, her uncle got his PhD in philosophy from Syracuse and became a mailman. And so I'm like,
yeah, as he should as well.
Maybe job prospects in the PhD in chemistry.
No, you should be happy with that decision process. I can tell you.
Yeah. All right, so we're done with the room. I'm going. Oh, thank you, Earth, but you can turn that off now. Okay, sorry. Yeah. So I brought us in with the song Drive by Joe Bonamassa, and I'm going to sing us out using Slow Gin by Joe Bonamassa, and I hope you enjoy that. Thank you guys. Thank you all for being here, and I hope to see you Wednesday, Friday.
Thank you, Sam, and
next Monday.
Good comeback.
Thank you. Thank you. I appreciate it. Have a good week, everyone.